Today it's my honor and privilege to introduce to you Dr. Untitled, who is this year's recipient of the George Ellery Hale Prize for outstanding contributions to solar astronomy. The Hale Prize is the highest award that's given by the Solar Physics Division of the American Astronomical Society, and it's officially given at the American Astronomical Society meeting this year is going to be Pasadena, whether or not we're meeting jointly with the AAS. The official citation for the prize this year is that is given to Untitled for his exceptional, I'm quoting from the committee, for his exceptional leadership in developing multiple, innovative, high-resolution telescopes and interpreting their data to dramatically advance our understanding of the sun, and for his generous public service on behalf of the solar and solar terrestrial communities. Since at the AAS meeting he will officially be getting the Hale Prize medal and check and so on, and that will be visually presented. However, the Solar Physics Division did not want to be eclipsed by this, and so we would like to present something else to Alan at this time. If you'll come here for a minute. And this is a tastefully wrapped prize. Yes, you have to hold it up too. Yeah. In case you can't read it, I think it says, I made outstanding contributions to solar astronomy and all I got was this lousy T-shirt. You all are here to listen to Alan and not to me, so I'll make my introduction brief, although it was very difficult because I started with Alan's veto, which is a really weighty document and then extremely daunting. If I may generalize, Alan's career has been guided in part by his love for all things mechanical. Reliable sources inform me, however, that his fascination with technology has not always been an asset, in particular his preference for fast sports cars. Just as one sterling example, driving recklessly on mountain roads with one's thesis advisor in the passenger seat is not really the route most of us would have taken if we wanted to impress our advisors, unless we knew that the advisor really enjoyed getting car sick. So, Alan began his education at Columbia and UCLA, obtained his PhD under Layton at Caltech, and then went on to postdoctoral work at Harvard, and where he got his first position of authority on a spaceborne instrument, the Skylab ATM H-alpha experiment. Since he joined Lockheed Martin 30 years ago, he has not only been instrumental in developing and implementing an astounding number of both spaceborne and ground-based solar instruments, but also in accumulating and inspiring a world-class group of scientists, engineers, and technicians. He has been a principal investigator on just about everything from SOUP to Solar B. For some reason, nobody named anything nuts, otherwise I would have had a great line. And has ground-based and has also worked on many ground-based solar observing instruments, including the Las Palmas, most notably recently, the Las Palmas instruments, adaptive optics instruments. I won't even attempt to describe his scientific accomplishments because they're all better served by his numerous publications. I'll just mention one of the most recent and one of the most exciting, which is the discovery of the magnetic carpet. In addition, Alan has devoted an incredible amount of his time to public service by serving on MOGs, NASA review panels, National Academy of Sciences committees, science definition teams, oversight committees, the latest 2 decadal surveys now, and a host of other activities that I can tell you definitely take time away from your research and from your own life. I particularly appreciate as a numerical modeler that Alan has consistent interest in theory and simulations, that he's insisted on including this vital component in his experiments, and I appreciate also his perpetual efforts to keep the theorists and modelers honest by enabling such distressingly good observations. The open data policy on TRACE is yet another example of his extreme generosity toward the solar and space physics communities. So on behalf of the SPD, I'd like to introduce Alan to speak about the science of the sun. Thank you, Alan.
Judy, you're all going to be very disappointed that the real Untitled is nowhere near as interesting as Judy makes him seem. Almost everything I say today can be found on our website. And most of what I say will be in the form of a video presentation, and I'd like to introduce that. First, I'll show you the sun from the core to the earth in about 2 minutes. Then talk about helioseismology, a relatively new science, 2.5 decades old, that allows us to actually see inside of a star. Fascinating. Then talk about the origin, disappearance, and dispersal of magnetic flux on the sun, the impact of magnetic fields on the outer atmosphere, and finally, talk about cool gas, horizontal fields on the sun, and we'll end with some violence. You can't have a good movie without doing violence. If nothing else, I'd like to get some points out of this movie, or at least what I'd like to do is lead the audience. And the first point, the most important point, is that joint advances in observations, theory, and numerical simulations are creating a revolution in our understanding of the sun. And one of the key words is creating. We don't have a revolution yet. We're creating a revolution. One never knows how revolutions turn out. Some revolutions are started with good ideas and end up terrible. I think ours will turn out great. Part of the revolution is being caused by the fact that about 50 active regions of magnetic flux emerge on the solar surface every day. So the quiet magnetic field of the sun is replaced in less than a day. And all of the solar flux is replaced in less than a month. The magnetic field is probably, and it's only said probably because I haven't actually measured it, but I think that any respectable plasma physicist would tell you that gyro radii are on the order of meters, and all we can see down is to hundreds of kilometers. But no telescope in the visible UV, EUV, or X-ray has ever clearly resolved structures on the sun. Whoops, don't do that.
Let me put this in.
Okay.
We can hear you better.
Great. This resolution and fine structure is important, not because it's pretty, but because it means that there's no line of sight through the transition region or corona, and probably the chromosphere, that can be described either by a temperature or a density. So when we look at the sun, we look at the sun's outer atmosphere, we look at a medium that has multiple temperatures and multiple densities on any line of sight. The width of these magnetic loops doesn't tend to increase with distance from the solar surface. So this fine structure is not something that's limited to close to the surface of the sun. It occurs throughout the atmosphere. Any astrophysicist then should be very concerned looking at the atmosphere of any kind of star that you suspect has a magnetic field, that you should be always aware of the fact that you're not looking at a uniform temperature or a uniform density medium. Furthermore, the majority of these loops are nearly uniformly heated, nor in the steady state. This is an essentially dynamic phenomenon. This lovely picture of an X point tells you that the 3D structure of magnetic fields is critical to understanding the rapid energy release processes that we see in the sun. And because magnetic flux is continuously emerging on a range of scales, this occurs everywhere and all the time. There's some major questions that this requires answered. This is what I'd like our revolution to start at least. How and where is the solar magnetic field generated? What is the relation between the surface emergence of flux and flux generation? We look at the surface, but that doesn't mean that the solar magnetic field evolution is fundamentally a surface effect. How do the small and large scales interact? I hope this movie will show you that there's a kind of inverse cascade on the sun. The magnetic carpet continuously interacting with larger scale structures and putting energy from small scales into large scales. What controls the scale of magnetic instabilities? And finally, to what extent are the violent energy release processes that we see predictable? And in the movie that I'll show, there are a number of institutions, experimental institutions and theoretical institutions, numerical simulators that have contributed. And finally, I have to talk about the team. This prize is given to me as sort of a chief scout. I don't think I'm the coach or the manager. I know I'm not the manager. But there are a lot of people, both scientists and engineers, who contribute now and have contributed continuously over 3 decades. And this is a very small fraction of the list. And this is to whom the Hale Prize really belongs. And finally, we all live in the sun's outer atmosphere. Phenomena that occur on the sun impact us on Earth, and usually in about 32 hours. In violent events, it may only be 8 minutes. And with that, I'll start the movie. And I'll turn this thing off. Now, John Leibacher knows that I really can't operate a laser pointer and talk at the same time. And so, please don't laugh too hard, John, if I fall off the stage. Because it will be really sad. This will start. I tried it before. The sun is a resolved star. It's the only place we can do problems of astrophysics that involve magnetic fields on an astro and really have a chance to see what's happening. Experiments like Super Kamiokande can actually measure and observe the neutrino flux of the sun. And we can test what the nuclear physics is. GONG and MDI and other experiments can measure the interior of the sun, so we can know the temperature, density, rotational structure of the sun. Now let's see if I can stop this. We can make images of the solar surface. This is an MDI image, and see sunspots. And those sunspots blend into magnetic fields, are sites of magnetic field, but the magnetic field extends well beyond sunspots. This is also MDI. Going into the chromosphere, this is a H-alpha picture from Big Bear. This is the transition region seen with EIT. Then is going through successively higher temperatures. These are all EIT images. This is the Yoko image at 3 million degrees. And LASCO that shows that events on the sun propagate out through the outer atmosphere. Can draw cartoons, and we can measure the particles impacting the Earth's magnetosphere. We can do numerical simulations to predict how it responds, how the magnetoscale responds. We can put imagers in space and look at the effects induced by solar particles on the Earth's atmosphere. And finally, these events can be observed on the ground. So as I said before, we can measure the temperature, pressure, equation of state, internal rotation, convection, and something about dynamo action. And we do this with movies of the surface that show millions of modes. And these modes are oscillating on a range of scales. In this cartoon, we can show that some modes penetrate deeply through the sun, others are rather shallow. And by discriminating between these modes, we can learn about the conditions along the ray paths. And by forming combinations of those, we can isolate individual layers. This is the data that we get, plot frequency against spatial order. Spatial order is related to distance. So we can probe the entire interior. And this is a plot of rotation, where rotation is faster at the equator and slower at the poles. And let's stop here. This remarkable plot that first emerged 5 or 6 years ago and has been refined subsequently shows that rotation in the sun throughout the convection zone is pretty nearly uniform, so that one could put a stick into the sun if it didn't evaporate or dissolve, and a stick inserted at a given latitude wouldn't distort very much. But there are two critical regions. One, the region between the radiative zone and the convection zone, where there's a lot of shear, and more than that, there are a range of different kinds of oscillations, which I don't have time to talk about now. There's also another shear zone near the surface. The shear zone is only 5%, but it has about 40% of the pressure drop across the solar atmosphere. And so a lot is happening in this region, and as you can see, the surface is rotating at a considerably different rate than the convection zone immediately below it. So it makes you be very concerned about what magnetic field does that's generated deep in the convection zone and is apparently fairly stationary on the surface. Let's make this go. And so this is a cartoon really, produced by ESA in fact, of what's happening just below the convection zone, the faster rotation at the solar equator, pulls magnetic field lines. They become more and more dense, so the flux per unit area increases until they're pulled up or become buoyant. This is a numerical simulation of how a flux tube might emerge through the surface. And when it appears in the surface, it appears as one of these wonderfully complex sunspots. One of the truly amazing and exciting things that have come out of MDI and ground-based research is that we can now actually image sunspots below the surface. So this is a sunspot. The colors are the magnetic fields. We can make a map of the sound velocity variations below the spot. And if you average azimuthally, you can make a somewhat better picture, and also you can put arrows on it and get some idea of what the flow systems are in and around the spot. People who do numerical simulations, quite remarkably, if this is playing, so this is a numerical simulation. And The topology of the flow system is remarkably similar. The temperature structure is remarkably similar. It's a real accomplishment to begin to get convergence of these numerical simulations. The numerical simulations predict an outflow around the spot at the top and an inflow immediately below on the surface. We can actually see that in sunspots. But we have even more clues. If we look in the chromosphere above the spot and we make a velocity map, we can see in regions of the umbra there's one kinds of waves, other kinds of waves in the outer reaches of the spot. And from these wave diagnostics, we can learn something about the field in the outer atmosphere. This is going a little bit too fast, or I'm not talking fast enough. This picture of the sun, of the sun's magnetic field, where black is out of the board, white is into the board, shows not only locations of sunspots, but a mixed polarity everywhere on the sun. And we can follow this group and zoom into it and see sunspot field emerging. The action of large-scale convection on the sun spreads out this field, disperses it over the solar surface. If we look now inward instead of outward and zoom in, we can see how this magnetic carpet comes to pass. Let me stop this again for a second. Each one of these circles is 30,000 kilometers in diameter. Every time a circle appears, a magnetic dipole will appear inside of it. So a new circle and a new emerging magnetic dipole. This process occurs virtually everywhere on the sun and is sufficient in quiet sun to replace the total magnetic field in just a few hours, somewhere between 6 and 10 hours. And if we zoom in even further, we can see inter-network fields emerging on an even smaller scale. These magnetic fields are embedded in the downflow regions of the convection. So this picture, which is 30 arc seconds across, tick marks are arc seconds. 1 arc second is about 700 kilometers. So these structures are a couple of hundred kilometers thick. They're in the downflow regions of the convection, and they stay in the downflow regions of the convection, and they're buffeted. And so every magnetic field line, every one of the loops that we see in the outer atmosphere is attached somehow, I don't know how, to one or more of these little magnetic field elements. They're evolving and moving on the time scale of minutes. That we've reached a state that we can actually follow the evolution in time of one of these structures. This little bright structure here is a site of magnetic field. And you can see how the granulation around it buffets it. It fragments, it merges, fragments again. So this is a continuously evolving process. At the same time, our friends in Cambridge can do numerical simulations of this process. So the green stuff is the magnetic field. And what these numerical simulations do is allow us to predict what happens below us in the surface, above us in the atmosphere, predict the existence of waves, and so the experimentalist can observe these things and go smile at people like Judy Carpet and say, well, you almost got it right. But what's remarkable is that that's true. They almost do get it right. This remarkable numerical simulation is a Boussinesque simulation at very high Reynolds number, and it actually shows generation of magnetic field, a sustained dynamo action in a model, which may explain why we see magnetic carpet effects. This numerical simulation is a simulation of supergranulation. Computers are now getting big enough and people clever enough to be able to attack the whole sun at least some level of resolution. This takes a tiny bit of explaining. This is a MDI map of the divergence on the solar surface. This is 30,000 kilometers. What we've done is we put test particles on the sun in the computer, and we've used the measured flow or the inferred flow to displace the particles. And on this side, we've just put the particles in at the beginning and let the sun do its trick. And on this side, we've continuously introduced quarks, test particles. And what happens is after a relatively short period of time, all the quarks are in the boundaries, and we can see what happens. This happens very rapidly. So everything is in boundaries after only 4 or 5 hours. But once they get into boundaries, they collapse. And so there are fewer and fewer sites where there are quarks on the sun. And this tells us what we should have known a long, long, long time ago, that the only way we can have mixed polarity on the sun is to constantly emerge it, and constantly emerge it very close to where we see it. These magnetic fields on the surface determine the structure of the outer atmosphere. This is a simple potential field calculation based on a magnetic carpet, and what you see here is an ensemble of interlaced loops, some large, some small. But this complexity of the surface field results in a very complex outer atmosphere. So this is looking at higher resolution following magnetic fields out through the outer atmosphere. And this is a movie taken by EIT for 2 weeks, showing how this large-scale structure evolves over periods of time. So these pictures are taken once every 20 minutes about. If we take pictures instead in every 30 seconds, you can see more complexity, more action, not surprisingly, because this has 25 times the resolution and about 50 times the cadence. And you can be convinced that this is a dynamic situation and that there really is no line of sight in the outer atmosphere that you could characterize by a constant temperature or density. This clock face is about the diameter of the Earth. These pictures are taken at a temperature between 3/4 of a million and 1 million degrees. And so what we're seeing is a slice in temperature space of the sun. If we were taking pictures at another temperature, a hotter temperature, you would see loops preceding these. These loops are cooling loops. They come into existence only as the result of cooling from hotter loops. With continuous observations, you get to see and observe in good geometries magnetic flux emerging occasionally. So this magnetic flux is emerging here. This region is on the other side, across the limb, 300,000 kilometers away. And suddenly, to the surprise of theoreticians, one sees loops appear, interconnecting loops, 300,000 kilometers away. And the presence of these loops seems to destabilize both of these regions and make them more active. This movie shows the passage of an active region across the disk. So it's 2 weeks long, and there's about 500 seconds between frames, just so we can show it in a relatively rapid time. What? Well, I guess you could call this lightning. It's certainly electrical currents heating and increasing the density. Right here, a new active region is emerging. And at first, it stays to itself, and it just sort of pushes the other active region away. But suddenly, there are reconnections. And you now have an interacting system of magnetic fields. This is exactly the same region at exactly the same cadence seen in our 1600 band, which shows the EUV continuum together with carbon-4. So these bright flashes are mostly carbon-4. Carbon-4 is formed at about 100,000 degrees. So things go through 100,000 degrees pretty rapidly. You get a very different picture of the sun. It's very clear that this 5-minute cadence isn't adequate for describing what goes on in carbon-4. This is a movie of the sunspots. This is roughly twice the scale of the previous movies and about 1.5 times the cadence. So this is the sunspot structure under the region that I've just been showing you in a week-long passage. This is where the region emerges. This region here. This is an interesting event. A sunspot collides with a previously existing sunspot, both of which have the same polarity. And if you watch the magnetic fields above them, they appear to rotate and restructure. This sodium will do it again. And at some point, the field lines sort of flip over the top. Right there. Somewhat surprisingly, a very, very simple model exhibits similar behavior. Stop this. The field lines are colored just to give you an idea of what field line is moving where. There's our sunspot here, and here's our moving spot here. And this is just a potential field calculation. And all we do, or all Carl Schreiber does, is run this magnetic field across into that one and watch what the field lines do. They rotate here, and then at some point flip over. So this kind of behavior doesn't require line tying. It doesn't require anything fancy. A potential field will do it. The loop-like structure that I've shown you in the previous movies is what you'd expect sort of from a potential field calculation. Of course, almost never are they in completely potential configuration. But what's very unexpected, although observed for, I guess, at least 150 years, are prominences Seen on the disk, they're filaments, and these have magnetic field structures that are parallel to the surface of the sun. They're seen in the EUV images that we're showing here in absorption. And so you can see fine structures that move at speeds from 30 to 70, 80 kilometers a second. They're very fine horizontal structures above the solar atmosphere that are in constant motion with cool gas in them. They form walls between regions of different polarities. Vertical walls of cool gas, 40, 50,000 kilometers high, that are in constant motion. The motions are always nearly parallel to the solar surface. And they're arced over by loops on a range of scales. Seen on the disk, you can see that they're active all the time. You'll see bright stripes, long excitations of magnetic field lines that don't just fall along the length of the filament, but go over the filament and are much straighter. And I think that that's an inference that above the filament itself, there's either a wall or a place for a wall of horizontal magnetic field that may rise up or may be there all the time. We really don't know at this point. But one can see that there's more order in this than just seen on the surface. And as you go to the limb, you can see these magnetic field lines that in this case are traveling about 250,000 kilometers, nearly straight, nearly untwisted, moving at velocities of 50 to 70 kilometers a second, parallel to the surface over long distances. And also you can see that loops arch over them. These filaments are interesting because sometimes they go unstable and launch 10 to the 16th grams or so of material out into the outer solar atmosphere and often reach the Earth. Excitations also travel rapidly across them and can excite other filaments that can go unstable, give rise to flares. And we'll end this with some flares. But before this is a flare that's very, very interesting. We're now seeing the post-flare loops. But what you should watch are these loops here and these loops here, because they'll go into oscillation. So here, and we'll do it again. See these loops oscillate. They're oscillating with a period of about 5 minutes. And they damp in about 5 cycles, which is only about 10 to the 9th times faster than would be predicted by theory. And so there's a dissipation mechanism here in this very highly conducting gas that we don't understand. It's of critical importance. This is the Bastille Day flare on the 14th of July of 2000. That was responsible for loss of the ASCA satellite. These are awesome and beautiful at the same time. This is a color composite trying to put together 3 of our temperature bands to indicate where the hot and cool material is. One of our temperature bands, the band at 195, contains an iron 25 and iron 26 lines, as well as iron 12, which we normally see. The higher excitation lines require sort of 10 to 12 million degrees to appear, whereas normally the 195, 193 lines are seen at 1 to 2 million degrees. We have another band at 171 angstroms that only has iron 9 and 10 in it. So if we see a pure green color like this, unblended by our 171 signal, we have reason to understand that it's 10 million degrees, not 2 million degrees. There are Yoko observations that corroborate this. But what's especially interesting is that this very high temperature gas doesn't seem to have the structure that the lower temperature gas does. This will move forward. On Easter Sunday, we were treated to another X plus flare, a series of flares, in fact. I guess we're getting some things that I thought I'd cut out of this tape. But we're going to get to see all of the April flares. In April of this year, the largest sunspot group in a decade crossed the sun, and we were treated to a large number of really interesting, exciting events. And maybe I ought to explain a couple of little things that you may have been noticing and wondering about in this picture. Let's see if we can stop it. Wow. It's doing it. You may have noticed these multiple arcs and point-like structures in a cross. The reason for that is that we're taking these pictures through a window screen. That we're looking at 171 angstroms here. That the detector that we have is sensitive to the visible, and this is down by a factor of about 10 to the 8th or so. And so the telescope has a sheet of aluminum in front of it, so visible light doesn't pass through. But unfortunately, this EUV light isn't very strong, and so the sheet of aluminum has to be pretty thin. It's about 1,200 angstroms thin, and it has to be supported by a screen. So what you're seeing here is the diffraction pattern of this screen. Now, that turns out to be a feature. If you're an experimentalist, any anomaly can be turned into a feature. Because these side lobes here are down in intensity by quite a lot from the peak of this diffraction pattern. And so by examining the side lobes, we can get another 2.5 decades of dynamic range out of our experiment. And we can actually see where the very brightest spots are. So when that went off, you notice that very quickly there were very compact X's. And so those X marks the spot of the highest energy release points. The other thing you'll notice is that periodically this picture has a kind of noise in it. Little spots everywhere. That's because TRACE flies in the sunrise-sunset orbit and goes through the auroral ovals once every orbit. And when it does that, we get electron impacts on our detector. And these are especially severe when the sun decides to do something nasty. And they're fast particles that get to the Earth in timescales of minutes. So this is the flare of the 15th, the X22 flare. There are ideas of how you heat the tops of these loops. These are torsional waves. being released from below the surface, proceeding up the magnetic field lines, and accelerating particles. Now we'll get the sun to do the same thing. These are filament ejections. Velocities of 200 to 400 kilometers a second. Density masses of 10 to the 16th grams. Kinetic energies of 10 to the 31 ergs. Potential energies on the same order. Not all of them go off. They're only going 300 kilometers a second. They don't have the escape velocity. Something has to push them off or accelerate them to 500 kilometers, 550 to escape from the sun. So a lot of these mass ejections, although they start at 300 kilometers a second, fall back to the sun. This is a numerical simulation of a quadrupolar flux configuration, ejecting a filament and accelerating it outward. This is a numerical simulation of the current density in such a system as the filament accelerated outward. So there are, even in these very complex situations, there are people who are doing numerical simulations that begin to mimic phenomena as complicated as that. And I'll end with the reminder that although it starts at the sun, we live in the sun's outer atmosphere. These violent events on the sun do propagate outward through the heliosphere in which we live, and they impact the Earth. And we can image the impacts on the Earth. And that's the end, or the beginning, depending on your attitude.